All right, hello everyone. My name is Mark Griffitts, and today I'm going to be going over a review session for lecture number 30, which was on heat capacity. So to start out here, we're going to briefly review what heat capacity is as a concept. And one good way to do this is to think about sand at a beach, if you're at a beach during a hot summer day, and you've got the dry sand, obviously, and then you have wet sand by the water, and you think about the temperature of each. And so when we ask, do you prefer to walk on wet or dry sand, obviously you'd prefer to walk on the wet sand because it's a lot cooler and doesn't hurt your feet. Anyway, so obviously the wet sand, but the question is, why is that? And it's because of the heat capacity of the sand, or more specifically the water that's in the sand. And for dry sand, obviously there's no water in that, so even though each is exposed to the same amount of heat, the sand with the water in it doesn't raise in temperature as quickly. And that has to do with the heat capacity of water. You can also find similar phenomena like this when you think about walking on pavement versus walking on grass. Even if both are exposed to the same sunlight all day, walking on grass is obviously going to be a lot cooler on your feet. And so what we say there is that it has a higher heat capacity. So we can read here that heat capacity, or C sub P, is the amount of energy which is needed in order to raise the temperature of an object by 1 degree Celsius. So when you have a higher heat capacity, that results in taking more heat or more energy to heat something up. Awesome. So here we have just normal heat capacity, and this is what we just discussed, and it's specifically an object. So it's useful for when we're talking about things that are quantifiable and not specific measurements of mass or moles. And so the equation to determine how much energy you need to heat something up is given by Q, meaning energy, is equal to the heat capacity times the change in temperature. So depending on how much the temperature changes, you're going to result in a different amount of energy that's needed, and that's related directly to the heat capacity value. We also have molar heat capacity, which is essentially the same concept, but it deals specifically with the amount of energy that's needed to raise the temperature of 1 mole of something. So that could be a compound, an element, pretty much anything. And that's also by 1 degree Celsius. So the equation for that is the same, except we also multiply it by the number of moles, which is represented by the N in that equation. And lastly, we have what's called specific heat capacity, and this is the quantity of energy which is required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And in this, rather than using moles, we just substitute the mass of whatever substance it is we're measuring the energy or the specific heat capacity of, and that's represented by that M variable there. So now we're going to talk a little bit about examples on how or when we use these things. We have an example here. It says a backpacker got 1.78 kilograms of water from a nearby river to drink, but needed to boil it first in order to purify it. Knowing that the heat capacity of water is 4.184 joules per grams degrees Celsius, and the initial temperature of the water was 23 degrees Celsius, calculate the total energy required to bring the water to boiling. So I invite you all to pause this video and perhaps go back to that last slide and see if you can figure out which of the 3 equations we want to use and what we would do in order to find that total energy Q. Awesome, and hopefully you've done that. If not, I'm going to walk you through the solution right now. So first we're going to use the specific heat capacity equation because we've been given a mass, 1.78 kilograms, and we've also been given the specific heat capacity of water as well as the initial temperature. We also are assuming here that boiling point is 100 degrees Celsius, so we can calculate our change in temperature from that. Here we have, you see I've converted from kilograms to grams just by multiplying that value by 1,000. So we have 1,780 grams of water multiplied by 4.184 joules per degrees Celsius. And then we have 100 degrees Celsius, which is our final temperature, minus our initial temperature, which is 23 degrees Celsius. And if you plug that into a calculator here, we get Q is equal to 573.5 kilojoules. So that's quite a bit of energy that's required to bring water to a boil. And yeah, that is essentially one way that we can use this equation. And it's also obviously possible to use if we've been given, say, the energy, and we're asked to find the amount of water, or we're asked to find the change in temperature. As long as we have 3 of the variables, we're able to solve for the 4th one. So it can be useful in many different situations. And so now we're going to talk a little bit about how this heat capacity applies to phase transitions. Because when you think about it, when you get something to a specific temperature, say water, you get water to 100 degrees Celsius, it starts to boil, but it doesn't all boil at the same time. It's not an instant process. Rather, as you maintain it at a certain temperature, you have to continue adding energy in. So what we see here is during a phase transition, such as ice melting into water or water evaporating into vapor, it becomes warmer than it never becomes warmer than that phase change point, the melting point or the boiling point, no matter how much energy you add to that. And that's because that energy is being used to convert the intermolecular bonds. It's being used to break those intermolecular bonds, and we're going to talk about that. It's actually called enthalpy. And so we have this phenomenon called enthalpy. When this phase change occurs, we're adding energy or we're subtracting energy, but it's maintaining a constant temperature because all of that energy is going into changing the state of matter rather than changing the temperature. So as I mentioned earlier, the energy either breaks or creates intermolecular interactions, causing the change of state of matter. So when we have a positive enthalpy, essentially, we are breaking, actually, hold on. Yes, we're breaking the interactions, and it's essentially changing it from either a solid to a liquid or a liquid to a gas. And then vice versa results in a negative enthalpy change because you're taking energy in order to create that thing. So an example here is we have ice, and you add the heat of fusion, or what's represented as delta H fusion, is equal to liquid water. And then we see here at the bottom, there's actually an equation for this, that the amount of energy required is equal to the moles times the value for the heat of fusion, or N delta H fusion. But here we're going to see that each phase change actually has a specific enthalpy value. We have the enthalpy of vaporization, or delta H vaporization, and that is specific to liquid to vapor, or vice versa. Now you'll see in that table there that when you're going from a liquid to a vapor, then the delta H is a positive value, whereas when you're going from a vapor to a liquid, that delta H is a negative value. And that's because, as I mentioned earlier, that delta H is representing the amount of energy that is being released or is being used to break those bonds. And so when it's going from a liquid to a gas, it's actually absorbing energy. Sorry, I might have explained that a little bit confusingly earlier, but when you're going from a liquid to a gas, that you're absorbing energy, and so it's taking energy in to be able to do that. It's an exothermic reaction. Whereas when you are going from a gas to a liquid, it has to lose energy. In other words, it needs to take energy into the system, or it needs to release that energy, and the system is losing that energy. Therefore, the delta H is negative. And that applies as well to the enthalpy of fusion, which is specific to a solid to a liquid and vice versa. And that's melting point. So now we're actually going to go over another practice problem, which is about the specific heat capacity, which we discussed earlier. And so what we have here is 3.79 grams of pure aluminum metal is cooled by water from 103.2 degrees Celsius to 34.8 degrees Celsius. The specific heat of aluminum is 0.890 joules per grams degrees Celsius. If the water started out at 32.7 degrees Celsius, how much water was used to cool the aluminum? So this is a bit of a different problem here. We're actually given a sort of system where we have two different specific heat capacities and two different substances that are changing temperatures. And essentially what we can do here is we know that the net energy is going to be zero. So we can write like this, that the energy that is created by the specific heat of the water is going to be inverse that of the aluminum. And then we can substitute our specific heat capacity equations in for that. So we have negative m c delta s, or c sub s delta t of water is equal to m cs delta t of aluminum. And so we've actually been given all of the information that we need except for a single variable. So again, I'd invite you all to pause the video and see if you can figure that out and isolate that one variable that we're missing. In this case, the amount of water that we needed in order to cool the aluminum, and see if you can figure that out for yourselves. Awesome. And so you see what we're going to do here is for the water we have been given we know the specific heat capacity. It's 4.184 joules per gram Celsius, as we saw earlier in this slideshow. We also know the change in temperature. Even though it's not specifically given, we see that the aluminum metal is cooled to 34.8 degrees Celsius. And so we also know that the water has to be at that because it goes to equilibrium. So we know that the final temperature of the water is going to be 34.8 degrees Celsius, and the initial temperature is going to be 32.7 degrees Celsius. So that's all that we know about that left side there. We're still missing the mass of the water, which is what we're solving for. And on the right, we have the mass of the aluminum, which is 3.79 grams, times the specific heat capacity, which is 0.89 joules per grams degrees Celsius. And then we also have the change in temperature, which is 34.8 degrees Celsius is the final, minus 103.2 degrees Celsius is the initial. And all we have to do there is a little bit of algebra, isolate that m, so we divide both sides by all of those numbers on the left there, as well as that negative. And what we result in is m is equal to 26.3 grams of H2O. And that's also equal to 26.3 milliliters, because this is water in this case. And that is a very useful way of calculating certain values when we're given a system in equilibrium, especially when we're given a system with water, because water is pretty simple to calculate, and that actually goes a little bit into calorimetry or calorimetry, which was discussed in another lecture. And lastly, I did want to also go over a phase change problem to kind of go over and help understand what was meant by the energy needed to put in to complete a phase change without a change in temperature. And so what we have here is, it says, we pick up some snow outside to use as a water source for oatmeal. Using 300 grams of clean snow at negative 15 degrees Celsius, how much heat do you need if you want the water to be 98 degrees Celsius when you make the oatmeal? So we want to think about this here. We're going to have a phase change because we're starting out with snow, which is ice or solid water, and that's at below its freezing point or its melting point. And so what we're going to find is that we're actually going to need 3 steps here. We have a step in which we need to heat it up to its melting point, and then at that melting point, as we saw earlier, we're going to have an enthalpy of fusion, and that enthalpy of fusion is going to be multiplied by the amount of moles that are associated with it, so that we can figure out how much energy is needed there. And then, get back here, we're going to need to figure out the amount of energy needed to raise it from 0 degrees Celsius to 98 degrees Celsius. And that as well also has a different specific heat capacity than ice. So we are going to have to be given those values, which are right here. As I mentioned, to find our total change in energy, we're going to need those 3 different equations. We need the one to heat it up to melting point, the N delta H fusion to fully melt all of the snow, and then the last one to raise the temperature from 0 degrees Celsius to 98 degrees Celsius. And so our first value is going to be 2.11 joules per gram degrees Celsius, and that's the value for ice. Our delta fusion, or delta H fusion, is 6.01 kilojoules per mole. We want to watch those units there as well. And then our last value in liquid form, we already know, is 4.184 joules per gram degrees Celsius. So I invite you all to pause the video one last time and see if you can figure out how to go about solving this problem here. And as soon as you've done that, you can come back and we'll see if you did it right. Awesome. So let us move on here. Cool. So I've got it all written out here. I'll just go over the steps briefly to explain the first part. The melting of the heating up of the snow to its melting point is going to be the mass, which is 300 grams of snow, times that specific heat capacity, which is 2.11. And then the change in temperature is actually going to be a positive 15, because we have 0 degrees minus negative 15 degrees Celsius. And that's going to give us 9,495 joules to warm the snow up to its melting point. And from its melting point, we see that we are going to have 300 grams, and we need to convert that to moles. So, the molar mass of H2O is 18.0 grams per mole. So just do a little conversion there, and we multiply it by 6.01 kilojoules per mole, which results in 100.1 kilojoules to fully melt that snow. I'm actually going to go back to kind of clarify this to make sure it's clear to everyone that when here, let me get my mouse here. Essentially, there are better pictures that I have forgotten to put into this. But essentially, you get up to this point, this melting point, and then there's just a buffer period, or a period in which you keep adding energy, but it still does not raise in temperature. And that's that period that we're at right now. Here is that we're currently melting the snow. So its temperature is remaining constant at 0 degrees Celsius, but we're increasing the energy so that it fully changes state or changes its phase. And so after we've added all that energy, after we've completely melted the snow into water, then we need to take that same amount, 300 grams, multiply it by the heat capacity of liquid water, which is 4.184, and also times the final heat, 98 degrees Celsius, minus the initial heat, 0 degrees Celsius. And that gives us 123,010 joules to warm the water up to the point that we can make oatmeal with it. Excuse me. And so lastly, we take those values and we simply add them up. And that's going to give us our final full amount of energy needed to take snow from negative 15 degrees Celsius and bring it to 98 degrees Celsius in a liquid form. And that's going to come out to 232.6 kilojoules. And lastly, I'd like to leave you guys with a few tips. This is actually a chart from the original slideshow, and it kind of helps out to know when we're given specific problems or specific things to solve for, which equation will be best. So first off, when heating an object, we're going to use the normal heat capacity equation, because all we need in that case is the heat capacity of that object times the change in temperature to know the energy. When we're heating a specific number of moles, we're obviously going to use the molar heat capacity because we have that number. When we're heating a mass, we first of all want to always make sure that's in grams. Then we're going to use the specific heat capacity. And then when we're specifically at melting and boiling points, we're going to be using our enthalpy equations. So for a solid at melting point, that's going to be the number of moles, again, times the delta H fusion value. If we're going from a liquid to a solid, that delta H is going to be negative. And then as well for the liquid to a gas, it's going to be the number of moles times delta H vaporization. And if we're going from a gas to a liquid, that's going to be endothermic, so it's going to be a negative value. And that is all for my presentation. Thank you all for listening. I hope you were able to learn a lot from this review session and hopefully go over some good practice problems. And that is all. Thanks for watching.